next we're going to talk about another comparison test that may be useful if you can't establish that term-by-term comparison that you need to apply a direct comparison test. So perhaps maybe a more simplified version of the function is not in the correct order with the a sub n and the b sub n for what you need to confirm a convergence or divergence. So this is the limit comparison test, and it says if we have two positive terms a sub n and b sub n, and the limit as n approaches infinity of a sub n over b sub n is equal to some constant that is finite and positive called L, then this two series here either both converge or both diverge. So if you can find a series that you know what happens to, and you can prove that the limit of the ratio of the two equals L, this means that one is not growing at a rate faster than the other asymptotically. So they'll have the same behavior. So for example, I have one like this that says the sum from 0 to infinity of 1 over the square root of n squared plus 1. So if I were trying to kind of simplify this down a little bit into something I can work with, I might let b sub n be the square root of 1 over n squared, which of course is 1 over n for n greater than 0, which we start with 0, so that works. I'm going to let this one be my a sub n. And we know that the sum from 0 to infinity of 1 over n diverges. This is a harmonic series, and it's a p series with p equals 1. So we don't really have to go through a whole lot more to show that. It's just what it is. So now I'm going to try to use the limit comparison test. I'm going to take the limit as n approaches infinity of a sub n over b sub n, which is going to be the limit as n approaches infinity of 1 over the square root of n squared plus 1, because that's my a sub n, divided by 1 over, let's use this format, the square root of n squared, just because it's going to be a little bit easier to work with. So I'm going to do keep, change, flip to simplify those fractions, and I'll have the square root of n squared over the square root of n squared plus 1. And of course, this is something that you could potentially use L'Hopital's rule with, or you could observe that you have the square root of n squared over n squared plus 1, and we know that that radical can basically come outside of the limit, and because these two have the same power, this is just equal to the square root of 1 over 1, or 1. So since it's a number L, since this limit has a value, and the function, and the series, the sum of b sub n converges, then the limit comparison test is going to say that, diverges. The limit comparison test is going to say that this series also diverges. So you can see I've just written out a statement stating that. And again, all of these pieces are important. We have to establish a b sub n, show whether it converges or diverges based on some of the rules that we already know. We have to find the limit and show that we get an actual finite number here that's positive also, and then we can just use the test. For this one, my a sub n is going to be a rational function, and I noticed that the difference in powers between the top and the bottom is that this one is 3 degrees higher than the top. So I'm going to let b sub n be 1 over n cubed. And the sum from 1 to infinity, and I'm just using the one that we started with. If it started with 0, and like in the previous one, you can use 0, of 1 over n cubed is going to converge because this is a p series with p equals 3. So that's all you need for that. So now we're going to take the limit as n approaches infinity of a sub n over b sub n. So that'll be 2n squared minus 1 over 3n to the 5th plus 2n plus 1, all divided by 1 over n cubed, which will be the limit as n approaches infinity of 2n squared minus 1 over 3n to the 5th plus 2n plus 1 times n cubed over 1, which is the limit as n approaches infinity of 2n to the 5th minus n cubed over 3n to the 5th plus 2n plus 1. Now you can either use L'Hopital's rule, because this is an infinity over infinity integral, limit, not integral, Or you can compare the powers, and since they both have a 5th degree power, this is just going to be the ratio of the coefficients, or 2/3. So again, since this is an L, it's a finite number that's positive, we can say by the limit comparison test, the series that we started with also converges. And one thing I want to point out, this number here, the 2/3 and then the 1 in the previous example, this is not the value of this sum. Okay, this is just proving that if we take this ratio of these two functions, then as the limit as n approaches infinity, it approaches an actual number. So it's not saying that this thing is going to converge to 2/3. We don't know what that answer is yet, and we really don't have a way to find it right now. For this one, we have the sum from 1 to infinity of n to the k minus 1 over n to the k plus 1. And I want to point out that this k minus 1 is in the exponent, and this plus 1 down here is not in the exponent of that one. And it's for k greater than 2, so this is defined and everything's positive, and we can use the limit comparison test for this value of k. So this is going to be my a sub n, and we'll let b sub n be something a little more simple. We'll use n to the k minus 1 divided by n to the k. So if I were to simplify this, I would have k minus 1 minus k, or n to the negative 1, or 1 over n, which of course we know the sum from 1 to infinity of 1 over n diverges because it is that harmonic p-series. So I'm going to take the limit of the ratio, a sub n over b sub n, so we'll have that n to the k minus 1 over n to the k plus 1, all divided by 1 over n. So I will keep change flip. And just be really careful and make sure you understand that this plus 1 is not in the power. So n to the k minus 1 plus 1 is what we'll have on the top. And then the bottom will just have n to the k plus 1. So I will have n to the k power over n to the k power plus 1. And this one is going to have, for whatever n is, you're going to have the same power on top and bottom. So this is 1 over 1, or 1. Therefore, by the limit comparison test, the sum of a sub n, which was n to the k minus 1 over n to the k plus 1, is going to also diverge. All right, one more of these. I've got the square root of n squared plus 1 over, the square root of n over n squared plus 1. I'll get it out one of these days. This is going to be my a sub n, and we're going to try to make b sub n a little bit more simple. Let's just kind of forget about that plus 1. So if it were the square root of n over n squared, that would be 1 over n to the 3/2 power. So this is a p-series where where p is equal to 3/2, and since that's greater than 1, this one converges. So I'm going to take the limit as n approaches infinity of the square root of n over n squared plus 1 divided by 1 over n to the 3/2. So that will be the square root of n over n squared plus 1 times n to the 3/2 over 1, which is the limit as n approaches infinity of n squared, because 1/2 plus 3/2 is squared, over n squared plus 1, which is 1. So by the limit comparison test, the sum from 1 to infinity of a sub n, also converges. Now keep in mind, I am choosing my B sub n based on what A sub n looks like. I'm just trying to simplify it down to something that I can work with and I know a rule for. You can't just pick any old function out of the air and make this work. It does have to be something that you know how to figure out the convergence or divergence of, and it has to be something that when you take the limit of that ratio, you're going to end up with a finite number. And it doesn't matter what that number is. I mean, it could be 100,000 as long as it is a finite number that's positive.